A consumer's preferences tell us how a consumer compares various bundles. So given a set of different bundles that the consumer could choose from, preferences tell us which bundle the consumer would choose. The budget constraint tells us what that set is going to be. So what is the set that the consumer is going to actually choose from? What we're going to do now is to look at how the consumer chooses from their budget set. So we'll look at this problem geometrically first with some pictures, and then we'll do the math. So consider the budget set that we had drawn earlier. So we've got this straight line from, you could either buy 25 units of good 2, or you could buy 50 units of good 1 if you only bought one good, or you could buy any combination of the two. Now let's consider this arbitrarily chosen point here, bundle D. That's a bundle you can afford. Let's draw your indifference curve through it. Happens to be indifference curve I1. Is this bundle D, is that an optimal bundle for you? Is that the best bundle that this consumer could have? The answer is no. All the bundles here, these are all better bundles for the consumer. In fact, any bundle here is better for the consumer, but the ones that are in the shaded area are bundles that are not only better for the consumer than D, but also bundles that the consumer can afford. So a consumer would not choose D when that was their budget set because they have all these bundles that are better and affordable. Okay, how about this point F? Is that the optimal bundle for the consumer? Well, no, because they can't afford it. It's not even in their budget set. So that wouldn't obviously be the choice that the consumer could make. Of course, if they could make that choice, they would, but they can't make that choice because it's not in their budget set. Remember, their budget set is comprised of the stuff in this triangle. So they have to choose from that triangle. Okay, let's try again. How about this bundle A? So what we've seen now, to be clear, is we saw that any bundle on the inside of the triangle, so any bundle that's strictly below this line, can't be optimal. Any bundle that's above this line, like F, is not affordable and therefore cannot be the optimal bundle. Can't be what's chosen. So what's chosen has to be on this budget line. So let's look at this point A. Could A be the optimal bundle? No, because you could walk up the budget line. These are all still affordable. These are all affordable bundles. Yet, remember, this I1 is the indifference curve that passes through both D and A. And all the bundles here are better than D and A because they're above this indifference curve I1. Similarly, B is not optimal because you could walk down from there. All these bundles are better than B. What about E? E looks pretty good. Well, whether we walk up or down, we're going to be making the consumer worse off. We're going to be moving to a lower indifference curve. So E is indeed an optimal bundle for this consumer. If we look at any other bundle that's affordable, anything in this red triangle, none of it is above the indifference curve I3. So all of these bundles that the consumer can afford have to be no better than E. So E is therefore an optimal bundle for this consumer. What we have here is that we have tangency. This indifference curve, I3, is tangent to the budget line. So at this point E, they have the same slope. In other words, the marginal rate of substitution, remember, is the slope of the tangent to the indifference curve, is equal to the slope of the budget line, which, remember, is the marginal rate of transformation. So if the marginal rate of substitution and the marginal rate of transformation are equal, then you've found yourself an optimal bundle. We could rearrange that. So just look at this part here. We could rearrange that. We could cancel out the negative signs and then just do a little rearranging to end up with U1 over P1 equals U2 over P2. Now let's interpret this optimality condition, or this tangency condition. So we've found this condition. So let's look at the left-hand side of this equation. What it tells us is, let's look at the numerator, u1. Remember, that's the marginal utility. So the marginal utility is the extra little bit of utility you'll get if you buy one more unit of good one. Now, P1 is the price of buying an additional unit. Now, how many units can you buy if you spend $1 on good one? Well, you can buy 1 over P1. So if your per unit increase in utility from good one is U1, then if you spent an extra $1 on good one, how much extra utility are you going to get? Well, you're going to get U1 times the amount of the extra amount of good one that you bought, which is 1 over P1, which is U1 over P1, which is that. So I'm going to call this the bang for your buck from spending money on good one. So it's the bang being the extra value you get per extra dollar you spend. Now the right-hand side is the same thing. It's the bang for your buck for money you spend on good two. Now let's suppose you were at a point, you picked a bundle where the extra value you get for spending the last dollar you spent on good one is greater than the last dollar you spent on good two. Well, what does this mean? Well, it means that you're not at an optimum, because you could take away that last dollar you spent on good two and spend it on good one instead. You're going to get a better value for your dollar from good one than you are from good two. And so overall, you're going to be better off. You're going to gain more than you lost. What if U1 over P1 is less than U2 over P2? By the same reasoning, you couldn't be at an optimum, because you could take money from good one and put it to good two, and you'd be gaining more than you lost. So you could do better. So it's only when the two are equal that you can't do any better, that you're at an optimum. This tangency condition defines optimality. U1 and U2 are going to depend on two variables, Q1 and Q2. So we've got an equation here with two unknowns. After all, we're trying to calculate the optimal bundle Q1, Q2. To solve for these two unknowns, we need two equations. What's the other equation? Well, it's just your budget constraint. Remember, Q1 and Q2 have to satisfy the equation P1, Q1 plus P2, Q2 equals Y. Of course, P1, P2, and Y are all knowns. So with these two equations, we can solve for the two unknowns, which are Q1 and Q2, which will often represent by Q1 star, Q2 star, the optimal bundle. We'll do an example a little bit later.